Hello, could you hear me?
So
Okay, how was your exam? Hello,
it was good. So
okay.
regarding that, will you be keeping any crips of sorts?
Well, time is not there because online the cribbing is difficult. What you can do if you have any doubt about the answers and the marks what you have got, you have already got the marks, na, question wise. Okay,
So
so
yes, sir.
so So you can write to that the student volunteer is there, na, Aditi Singh. You can write to her. Then I would answer. If you have any queries and all sort of things. This is one way to do it. And actually, we have two more classes. This one and the Monday's one. Okay. Where 19th is the last class, na? 19th means as far as we are concerned. Am I right? 20th is the last class, right?
Yes.
Okay, so our
28th is the last day of instruction.
yes, so our last class will be on Monday. So if you wish, if you have any queries, we can discuss it on Monday. That is another way to handle it. So let me finish it, whatever I could finish today. Then Monday we can clarify the queries if you wish that way. Or I would continue Monday to cover a few more slides the way you would like to. So you let me know accordingly. So this is one option, and the second option is regarding quiz. Most of you have done reasonably well. Some of you have done very good. Not everybody has done very good. So you can check your answers. If you feel that it was not properly marked, you deserve more marks. Don't tell if you deserve less marks. Okay, but if you deserve more marks, so please share to Aditi, and I would look into it, and then question-wise I would try to answer it. But that would be at the individual level, not as a whole. But if you would like to have a general discussion regarding the course, then Monday we can do it. Okay. So you let me know whether you wish me to do that discussion on Monday, or you wish me to proceed on further on the topic of the catalysis, what we have been, exploring right now further. So you let me know, and accordingly I would follow. So, okay. And remember that your NSEM, I think I have checked the NSEM timetable 5th of May. So it is 8:30 to 8:30 or 9:30 to 12:30, something like that. But in our course, your exam is not the 100 marks exam, na? It's only 40 marks exam, because already 10 we have taken care of. So rest is 40. So this 40 we will do it in 2 hours instead of 3 hours. Okay. To think about it and all these things. Okay. Should I begin or should I wait for the other students to come or to join? Hello.
I think you can start.
Okay.
Sir, I had a doubt. I had a
Yeah.
request actually. So
Yes.
if you can provide the model solutions, it will be easier for us to ask whether our questions are right or wrong.
Model answer.
Yeah.
Well, that I will give it in the end same. Okay. So model answer again, I may not get enough time to write down all these things. So what I am trying to say, you have question in front of you. I don't
Uh,
have the question in this computer. I have in the other computer. You have the question with you?
yes, sir.
Could you tell where you have some doubt? Then I can try to answer it.
I mean, I don't have a doubt right now, but like I'll have to check the answers and like
So
try.
that's why I'm saying. That's why I'm saying. So Monday, okay, let us have the discussion session on Monday, where regarding the quiz questions. If I'm not talking only to you, to everybody, if you have any doubt regarding any particular question on quiz, then I will try to answer all the queries. Okay, this is the first point. Second point is, in general, whatever we have covered so far, if you have any doubt or if you have any clarification, I will do it on Monday. Is it okay?
Yes, sir. Thank you.
Okay. And end same, what I will do, end same, I will write down the model answers properly, and that I would put it up to the site. And then after, and of course, after your exam, then when you will be getting the marks, you can match it. And you can see whether I have made any mistakes or you have really made the mistakes. And then accordingly, if you have any doubt, okay, I will be available. So we will try to fix that problem either at our site and or at your site. So that can be done at the end same. And I thought the quiz, all of you would be doing very good. So I just I did not make the model answer, but Monday we'll discuss it. Okay. Okay, let's see if I could manage to have some time, then I will put up the model answer in the site. Okay, so I'll try it before Monday. Now, what we are trying to talk about the issue of catalysis. Last day, I think we talked something about the catalysis. It's a vast field. We are not entering into the vast field. We are only entering into the domain where you can get some perception about the point of catalysis. So in the due course of time, you will have enough courses to go through the catalytic events, etc., etc. I only, just to recapitulate, to make few points, I only said that, that industry never bothers about the stoichiometric reactions, either at the organic part or at the inorganic part, what we do in our laboratory. Okay, not only the things what you do in your practical classes, but also what you do during your, you will be doing later on during your research work also. There we only think about the fundamental aspects of the reactions, of the processes, so many things we try to cover up, but those are equally important. But industry looks at everything at the catalytic way, because they are dealing with not only the processes, they also discover a lot of new processes. Of course, there are many good industries. They develop a lot of processes parallel to your academic institutions. And unlike academic institutions, they also produce the required items for the society. Okay, and they produce in terms of tons and all sort of thing, and their stoichiometric does not have any place. They need to only do it by catalytic way. And also in the biology, you know that there are so many enzymatic catalytic processes it does it. And there I said there are three primary divisions within the catalytic processes. One is the homogeneous catalysis, other is the heterogeneous catalysis, and other is the mixed, okay, the hybrid process, what is called homogenized heterogeneous process. Okay, so nowadays, at one point of time, industry used to look for the heterogeneous only. And in those days, they only used that aluminum oxide or your, silica gel support. On top of that, they use the palladium charcoal, platinum charcoal, Rennie nickel, all sort of things. But later on, they realized that homogeneous has a lot of advantages and disadvantages. Heterogeneous has a lot of advantages and disadvantages. They wanted to combine it and to get the best out of the lot. And you have noticed that I also mentioned the catalytic processes. You have two things to take care. One is the product formation in terms of percent yield, or in asymmetric process in terms of percent EE, or you need to also consider the fact of the selectivity. And as you have noticed that I said already, the catalytic processes, the delta G activated, that gap, the activation energy lowers and that gap recurs on 100 kilojoule. okay, per mole. Whereas selectivity requires very small amount of energy, yeah? So roughly 2 to 5 kilojoule per mole. And that is good enough to alter the selectivity, yeah? Say from D to L, L to D, or cis to trans, trans to cis, etc., etc. So it's a very sensitive process, and one needs to make a very delicate balancing between the process. Sometimes what happens, selectivity is so important, one could still compromise a percent of the yield. Okay, so you may get 100% yield without much selectivity. But selectivity, if it is too important, where selectivity is not so important, then you can concentrate only the fact of the yield. But if selectivity is equally or very important, then you can compromise the yield also. Yield may be 60%, yield may be 65, 70%, but your selectivity might be 99% or 98%. And that is how asymmetric catalysis moves on. Okay. And I also told you that asymmetric catalysis, one particular diastereomer or enantiomer maybe a very good medicine or drug, and the other enantiomer may be a poison. So if you mix together, your activity will be 50% only. Okay, but if you could separate them, your activity in one case minus, negative, minus means poison, in other case 100%. Okay, or close to 100%. That's why the separation is very essential. So catalytic route is the only route by which you could separate it. And this separation, it is guided by the parameter what we call the selectivity, and that is how you need to make a move. So and then we also mention that in catalysis we define in terms of TON, TOF, right? TON means turnover number. That means how many moles one could generate out of 1 mole of catalyst. That means how many cycles it can move on. If the law, and TOF is essentially divided by the time. So if the TON is very high, that means the catalyst is very good. Okay, in terms of yield I'm talking about. Okay, selectivity is a separate issue. Now you may develop one catalyst for a particular reaction. If the TON is not that bright, industry may not be interested, because economically that won't be very viable. So you have to take care not only the catalytic processes, okay, but also its turnover number. Now, for a particular reactions, what happened that if you generate one catalyst and you would see that catalyst is very selective for a particular reaction. It's not very generic that one catalyst you have in hand and it would carry out all the reactions. No, it will never work that way. That catalyst would be very selective for that is good. If one catalyst is good for everything, that means there is no chemical fun into it, right? So that's why for each and every process, you need to design one well-defined catalyst. That's why it's not very easy. To develop one catalyst for a particular reaction, it takes decades, sometime, if not more. And catalytic process normally we write in terms of a cycle, the way it has been shown over here. Cycle, because at the end of the reaction, you need to get back your catalyst so that that catalyst could participate in the second, third, fourth, and so on, so forth processes. And that's why the TON develops. Okay. Now, we started talking about this particular catalysis where we call it the catalyst for your isomerization. Okay. And if you notice the catalytic route in the cycle, all in equilibrium in process. That means it's a reverse process also true. That means a catalyst, if it is good for the forward reaction, the same catalyst could also be equally good for the reverse reaction. Okay, that one needs to be, needs to understand that point. Okay. Now here we are talking about, say, alkene. Now alkene could be internal, could be, terminal, right? Okay, for ethane, there is no question of internal or terminal. Nah? But if you go for the larger alkene, you can have internal and terminal process. Now you have one internal alkene and you want to get the terminal alkene for your certain, reactions or certain uses. Okay. Now, what kind of catalyst one could think about? Now, there are two ways to think about. One is the organocatalyst, other is the inorganic catalyst. Now, if you see the literature, you will be seeing a lot of organocatalysts are available. And those are mostly, I should say, academic interest or industrially for certain very selective processes. Now, what people have observed that metal-based catalysts are found to be the most effective one in terms of the percent yield, in terms of percent E, in terms of selectivity. Okay, and that's why the processes are very popular in a different sense. Okay. Now, also we mentioned that when we go for the metal-based catalyst, the two type of there are many catalysts are available based on the type of reactions you want to carry out. But in a general sense, we have noticed that metal hydride or metal carbon bond based catalysts are widely being utilized. Okay, there are a lot of reasons behind it. Okay, let us look at that this one particular metal hydride based complex, and this complex initially it is completely saturated. Now, if one particular compound needs to function as a good catalyst, then you need to provide some, coordinatively unsaturation into the system so the substrate can bind it. If it is octahedrally surrounded, then how does the substrate bind over there? So even if it is octahedrally surrounded, that could be considered as a pre-catalyst. I already said pre-catalyst is the form in which the catalyst actually sustained, but that is not the form which participates into the reaction. The form which participates into the reaction, that is called active catalyst. So that's why this octahedrally surrounded compound, what we have considered in the beginning, that is actually functioning as a pre-catalyst. Okay, and if you remove 1L, now the question is it so easy to remove? No, it is not so easy to remove, and that's why all compound cannot function as a catalyst. So the compound which having the characteristics of creating unsaturation, that compound could be good for the catalytic purpose. And that for catalysis, normally we have the bond making, bond forming processes, along with few more processes are operational, at least for the metal-based catalyst. One called oxidative addition, other is the reductive elimination, and your insertion or extrusion. These are the processes normally functional while dealing with the metal-based catalyst. Okay. Now, the compound which could participate in oxidative addition or reductive elimination, that does mean that particular metal ion which must sustain in at least 2 oxidation states in a good way. If the compound sustains in one particular oxidation state, that means that metal or metal-based compound cannot be a good catalyst. For example, iron 2, iron 3. Okay, nickel, if you take, nickel is very difficult to function for the catalytic process where oxidative addition or reductive elimination is needed. With nickel case, the nickel 2 is the only stable oxidation state, and the other 2 oxidation states of nickel 1 and nickel 3, both are very unstable situation. Okay, so they cannot, in general sense I'm talking about, not in all sense, that they cannot participate in catalytic processing. That means the metal has to sustain in at least in 2 oxidation state. So that's why iron is a very good component for catalysis. Or heavier metals if you take, which are having a lot of advantages because their hydrides or metal carbon bonds are normally stable, they don't undergo hydrolysis. and they can easily stabilize into three, oxidation state, or 3-4 oxidation state, or 1-2 oxidation state, like copper 1, copper 2, something like that. Or heavier metal, if you go silver 1, silver 3, but the problem is over there that you have to deal with your 2 electron transfer over there. Gold 1, gold 3, gold 2 is not very common. So these are the factors, basic factor you have to take into account to understand the catalytic process. So what is happening in the first step? One ligand gets out of the system. It creates metal hydride is there in the beginning itself, and it creates coordinatively unsaturated situation so that alkene can bind, and alkene can link to the metal center the way the Zeise's salt is formed. It was known in the literature since long. And once it is formed, then what is happening? Alkene now becoming alkyl by considering the fact of the this hydride transfer. Hydride transfer process takes place from here to here, and as a result, you can see the metal carbon bond is formed, and then beta hydride elimination takes place, and as a result, again you see that one hydrogen comes over here, one hydrogen transfer over here. So you can have the alkene bond over here. Look at the alkene bond, and then again this bond goes away, and you get back your active catalyst, not the pre-catalyst, active catalyst. So there are so many steps involved. Now you could argue, for the sake of the argument, what is the basis of saying all the points what I have mentioned over here. Now that is the good point, that you need to trap each and every intermediate. Okay, now how do you trap each and every intermediate? One point is, already you know this chemistry, general chemistry you know. Without understanding the general chemistry, you cannot figure it out, the catalytic routes or mechanism, right? So these are the common general chemistry as far as the organometallic chemistry is concerned. That alkene, how alkene can bind to the metal, first point. Then hydride transfer is one common reaction. Then metal carbon bond formation, another common feature. And then again that beta hydride elimination, another common feature. And then the product will get out of the system, leaving your this active catalyst back to the system again, and the cycle goes on, right? So each and every intermediate could be not isolated, could be trapped spectroscopically. Spectroscopically means that you have to carry out the reactions online, and the products would be, and the reaction, the channels would be connected to different spectrometers or spectrophotometers, and immediately it would record all the parameters over there. You need not to understand all the details. I am giving you the glimpse of it so that you can feel it. And then it will get the mass spectrometry, it will get the NMR spectroscopy, all sort of things, and you will be getting informations. And since you are being already experienced that what could be the spectral feature of this compound, what could be the spectral feature of this compound, what could be the spectral feature of this compound as a function of time. Now what happened? Sometimes reaction process very fast. You may not get the chance. Okay, if your experimental setup is not too sensitive to detect each and every fast processes, then you may end up with 1 out of 3 or 2 out of 5 intermediates. So then you have to just teach it, okay, by considering your chemical knowledge, and then you can draw the cycle. So you understood what I'm trying to say? I'm trying to say, ideally, it is necessary to figure it out, information about each and every intermediate, what it is written over here. But not necessarily your setup would be good enough to help you to trap each and every intermediate. You may get a fractional information, and then you put up your all ideas together. Ideas means the all basic and fundamental knowledge in this area you have put it together, and if you stitch it properly, then you can easily develop this cycle. Okay. Now you see, it follows to the beta hydride elimination pathway, right? Now, if you go for the reverse process means from terminal to the internal alkene, then you can also start with, because this way you can get back terminal to the internal again. Okay, but at this point, what is happened? The kinetics is in this direction, so you will not get it back over here. So you can start with a particular compound where there is no metal hydride. That is an alternate route. And here it is a saturated compound, so you remove one L, then you will have the unsaturation over here, and then terminal alkene, which will bind over here, and it processes through the allylic intermediate. You look at the allylic intermediate, and then hydride, and then in this process, one proton will come over here, and you will get an intermediate metal hydride, though you did not start with the metal hydride, unlike this process. And then the hydride transfer takes place over here, and you will be getting the internal alkene. So from internal to terminal, your requirement to start with the metal hydride, provided you pass through the beta hydride elimination pathway. Now, if you go for terminal to internal, you don't need to start with the metal hydride. You can start without metal hydride even, but then the mechanism would be you would pass through the allylic intermediate, and intermediate metal hydride would be formed, but that would be again transferred to the allylic center, and by that process you would be getting your internal alkene. So it's a rather complex process, but this is how it works. But organic chemistry wise it's simple, but catalytically it is not so simple to proceed on. Now, once you have this alkene, one should remember the point that internal alkene is thermodynamically a stable situation. Okay, terminal alkene is not thermodynamically favorable. So once you have the terminal alkene, always there is a propensity to move it to the internal alkene. And once it is an internal alkene, then remember you can have your butadiene, for example. You can have the isobaric product, that means cis and trans. So these are the issues you need to handle it. So once you are moving from terminal to the first cycle, previous slide, this slide, you see moving from here to here, or moving from here to here, you'll be getting the internal. Now I have written internal in the form of the cis. It could be also trans. So these are the factors you need to keep it in mind. Now another very common process in our system, that is called hydrogenation. Hydrogenation is one of the very, very important things. For example, all the edible oil what we use, so we have to be very careful about that. So if you hydrogenate it, then it will become vanaspati. Okay, you know that, So hydrogenation, there are so many reactions you will see where we need to remove that. We need to go for the hydrogenation process. That means alkene to you will be getting alkane in presence of hydrogen. Now it's so simple to write on a piece of paper. Just alkene plus H2, then you will be getting alkane. Or alkene plus H2 plus CO, carbon monoxide, you will be getting formylation reactions. And then ketoenol, tautomerism, all sort of thing. Now that's why I said academics is completely different, but without academics you cannot move into industry. Okay, so that question is how this hydrogenation takes place. Now there are many hydrogenation catalysts. Okay, mostly people use the rhodium, platinum. As I said in the beginning that in the periodic table, the heavier metals are considered to be the better candidates for catalysis or catalyst because of they are susceptible to hydrolysis, they can resist the hydrolysis process, and also they can resist the decomposition of the metal carbon bond, or they provide the stronger metal carbon bond compounds. Okay. Now, if I consider the rhodium one, look at this catalyst. Now, why this is a good candidate as a catalyst? If you see that this is a pentacoordinated rhodium compound, rhodium in one state. Okay, and you know that rhodium can stabilize in rhodium 1 and rhodium 3. Rhodium 2 is not that stable, though it is below cobalt. In cobalt case, you will be seeing cobalt 1 is not stable. So cobalt 2, cobalt 3. But rhodium case is a little bit different situation, but it's a very basic chemistry. Now, this is called pre-catalyst. Though it is 5 coordinate, still it's a stable compound, very stable compound. You know, we can make it our laboratory every day. So stable. Why it is so stable in spite of being 5 coordinated? Because of the umbrella effect. Umbrella effect means there are 3 phosphines, means essentially 9 phenyl groups. This rhodium is surrounded by the 3 phosphine, and 3 phosphine having 9 phenyl groups. That means it is covered the everything around the metal centers. And if we look at, this is 18 electron compound. So 18 electron compound is useless for any reactions, right? Because it's a very stable configuration. So if it is a very stable, you can, for example, if you want to change the mind of any of your friends, okay, and that if the friend is very stubborn, you know, you cannot change his mind. If he says yes, it is yes. If he says no, it is no. But if that your friend is little bit, you know, fragile, I'm saying fragile in the sense he is not that stubborn, okay, then probably you can give a good try to change his mind in your favor. Right? Yes, no, whatever it is. Similarly, in a compound, the compound which is having 18 electron configuration, you cannot do anything with that, okay, electronically. But then you have to think whether should you throw this compound out of the window. But you have to think about another factor which is in your hand. So always with a particular compound, remember this thing. This is like a Bible, that if you have a compound in hand, first of all, we don't make the compound to see that compound, nah? Because all compounds are poison basically. So still we make the new compound so that it can be used for the betterment of the society, right? Betterment of the human, human betterment, etc. Right? So we have to utilize the 2 factors parallelly. If one factor is not favorable, then other factor could be favorable for certain utility. Now this compound, if we take it as an example, this is 18 electron, this is useless, so it cannot do. But advantage of this compound, it is sterically in a very bad condition because of the 9 phenyl group. So this compound has the tendency all the time to get rid of one phosphine. If it throws up one phosphine, then it will become tetracoordinated. And tetracoordinated compounds under any circumstances expected to be reactive, and also it will be losing 2 electrons immediately. So it will become 16 electron compound like this. And you look at, instead of 3 phosphine, now you have 2 phosphines, and these 2 phosphines are trans in position. Why they are transposition? Because of reducing the steric bulk. So we played with the steric factor when the electronically there was no option. Okay. So vice versa. This is how one needs to play with. And you have one hydride, which is necessary for hydrogenation, right? So you need one hydride. You have now 2 phosphine. Now if you allow this alkene to react, it has enough space around it. Nah? It has now become tetracoordinated. If it is a pentacoordinated, 1 phosphine would have been here. Okay, so there was no scope of substrate. Substrate could have attacked from here, but what will happen? A lot of phenyl groups. These phenyl groups would cover this zone, even under pentacoordination. Now, if it tetracoordination, then enough space substrate can bind. Now you look at, as soon as the substrate comes into the picture, the trans-phosphine is going to the cis-phosphine. That means it is providing enormous space so that even this phenyl rings cannot come into the picture to stop the incoming alkene group over here, right? Though cis orientation of these two phosphine, this is not good as far as the steric factor is concerned, but this one is favorable. But what is happening as soon as the alkene comes, so steric is not favorable, but your electronically it becomes favorable. Now it is 18 electron configuration. Clear? Okay. So you have to remember that how the steric and electronic factor, they interplay so that one advantage could be exposed at least to carry out the reaction. Okay. Now once it is there, and also you have to understand that you are trying to do the hydrogenation. That means the hydride, what you have used, that is the point of concern to participate in the hydrogenation. So the hydride and alkene position should be cis to each other. And that is one of the reasons for which the phosphine went back to the cis position, even if it is sterically not favorable. And once it is in the cis position, then hydride transfer takes place. That chemistry is already known, hydride transfer. And as a result, what is happening now that this alkyl bond is formed, metal alkene bond is forming. So instead of the pi complex, you have now a sigma complex, right? Hydride is transferred over here, and this carbon is now linked to the metal center directly. Instead of the pi bond, you are getting sigma bond now, and then it is again remaining in rhodium 1. Okay, and you see that again, once this alkene bond is formed, it is again going back to the trans form, right? And then it is hydrogenation. Then you have to pump in hydrogen into the system, and as a result, what happened? Hydrogen will bind this way, and then this hydride will transfer over here, and you will be getting alkyl, from alkene to alkyl, and you get back your product over here. So there are couple of things are going on over here. One point is very clear, that hydride transfer, in order to undergo this transfer process, alkene and hydride, the mutual disposition should be cis, otherwise this transfer cannot take place. First point. Then second point, metal pi 2, you are getting metal sigma bond, alkene bond, and then hydrogenation, and then again one more step of hydride transfer, okay, to the alkene metal carbon bond or to the alkyl group, and as a result you are getting the alkene over here. Now you could argue, well, this could be kinetically followed and this should be the rate determining step. That's a separate issue. Now you could argue that on a piece of paper, what it is written, that in some steps you would see that phosphines are in trans, some steps you see the phosphine are in cis. How do you prove it? Is it just the whimsical aspects of the author to write this way or that way? Absolutely no. You can prove it very, very clearly. You can prove it by IR spectroscopy. If it is cis, you will be getting, or NMR will be better. You can record the 31p NMR, 31p I value equal to half, and that is NMR active. Okay, and then here in case of trans, both the phosphine will be equivalent. Okay, so you will be getting one signal, but in case of cis, you will be getting two phosphorus signal, right? So if you do the in situ NMR operation, 31p NMR, not proton NMR, 31p NMR, then you will get all the information over here. Now, if you go for proton NMR, then here you will be getting metal hydride signal resonance, and here you will not get any metal hydride resonance, right? On the other hand, you will be seeing metal carbon bond here in the carbon 30. So you need not to understand all the things what I am talking about. I am just trying to give you the give an idea. Okay, you need to understand this part, but the detailed spectroscopic aspects you need not to understand, because that you will be understanding slowly, not today. So but I am telling you that whatever it is written over here, everything could be possible to prove experimentally. So you can keep a lot of confidence on the way the cycle is being drawn, because you'll get the cycle in any book. Nah? These are all well-established cycles. So, so you have to start with the metal hydride, then alkene metal carbon bond formation, just like the Zeise's salt, and then hydride transfer. We know that hydride transfer process, how it works on. And then once the hydride transfer takes place, you get the pi bond, metal alkene pi bond to metal carbon sigma bond, and then hydrogen attack. Again, you have these 6 coordinated species, and you see the phosphine are in cis position now. And this carbon monoxide, it is basically an ancillary ligand. It is of no use as far as this particular catalysis route is concerned. Now, how do you prove it? That this carbon monoxide has of no role over here. You can prove it by following the IR spectroscopy, okay, or even the carbon-13 spectroscopy, and you will see the metal carbon, that resonance, okay, that would remain more or less intact, more a slight variation because of movement from here and there, but it remains intact. And also the IR CO vibration is very prominent. Everybody knows it. It comes out 200 centimeter in, but very strong vibration, and that vibration would remain intact more or less with slight variation here and there. Okay, so all steps could be very nicely followed. Now, if you go to the next step, now remember one thing also, that when you try to hydrogenate, okay, now hydrogenate of terminal alkene, okay, that is the way it should go on. Then you can hydrogenate it, right? And remember also that isomerization is a process of this hydrogenation. So you may get internal alkene, and once you get the internal alkene, then again it could isomerize to the 2 positions to 3 positions and all sort of things. So you may be getting 90%, say, your alkyl, okay, alkane from alkene through hydrogenation route, but you may be getting a small amount of alkene. Now, if your catalyst is not good, you may have the reverse pattern of the products. You may be getting 40% alkane and rest 60%, maybe 30-30 or 40-20 or 50-10, the other alkene, okay, that means your catalyst is not good enough. So you have to modify the catalyst. Okay, once you understand that this catalyst is good to proceed, but this catalyst is not good to stop the searching. Okay, then you need to search for the new catalyst, and then you may end up with a catalyst which will be very selective, not the isomerization, but the hydrogenation. Okay, because here your target is not isomerization. In the previous case, your target was the isomerization. So there you have to choose the catalyst in such a way, so there is no question of hydrogenation, only your isomerization. But of course, there you did not pump in hydrogen gas, but for hydrogenation you need to pump in hydrogen gas. That is one of the differences. But the catalyst, even if you pump in hydrogen, then if your catalyst is not good, then instead of getting good amount of hydrogenated product, you will be getting much lesser amount of hydrogenated product, but mostly your isomerization product. So you have to play with that. Then at one point of time, and this particular catalyst, what I have shown, the rhodium base, that's a wonderful catalyst. You can get yield up to 100% to get that. That is why this is the textbook example. Many other reactions are there which are also equally good, but all reactions cannot come to up to the level of textbook. Textbook means there is no side product. It's a pakka final product. Okay. Now, if you like to go for hydroformylation, you look at the same catalyst. Same catalyst could also be used for hydroformylation. Okay. Now hydroformylation state is nothing very much different, and you know the hydroformylation reaction. No? I have shown you the reactions. Just a second. You look at this. Yeah, this is the step. So hydrogenation, you are only using hydrogen, right? And hydroformylation, you are using mixture of hydrogen and CO. You are getting aldehyde, or then you can do the ketoenol, tautomerism, etc. Now, if you go for hydrogenation, this step is again same what I said. This is the pre-catalyst, a very stable compound, cannot take part directly into any catalytic processes unless and until you break one phosphine group from the catalyst surface. So remove one phosphine, you now get tetracoordinated species, and this is rhodium 1, 16 electrons. 16 electron is not stable configuration, so it will immediately try to bind with something. And here the geometry is such the phosphines are in transposition, enough space is there, this side or lower side, so alkene can bind very easily, and it is linked to metal in such a way. It's a wonderful reaction. Chemistry is really wonderful. It binds to the metal in such a way that the hydride and alkyl, they are in a very suitably defined position, that is a cis position. If it would have been that hydride is trans to this alkene, then you cannot imagine any hydride transfer, but it has to be transferred. So their close proximity is very important. And in a chemical sense, close proximity means we understand the cis position, right? And that is how it is being. And that's why it's a fantastic catalyst for hydroformylation as well. And then hydride transfer, like before, what I said, you get the alkene bond. So up to this, everything is same. Now here what we are doing, that after that, in the hydrogenation process, if you go to the hydrogenation process, after this, you are pumping hydrogen, right? And then you are getting the product. Now here, instead of pumping hydrogen, you are first pumping CO, carbon monoxide gas in the system. So CO again is a tetracoordinated. CO can bind over here. So you see pentacoordinated species. This is 18 electron system. Now the way we have considered hydride transfer, same way it is known in the literature, which this company did not discover. Well, who discovered? In the laboratory, research laboratory, it was discovered the carbon monoxide migration to the metal carbon bond. Carbon monoxide migration to the metal carbon bond, and you look at from the pi bond, from the metal pi bond. Here you have the metal carbon bond. This is a sigma bond. And sigma bond means single bond. Single bond means that insertion is possible. Now there are two phosphines. You look at, two CO group here. Now the previous CO group, you look at the previous CO group, which was trans to the hydride group. Here it is cis, but after alkene formation, it has been it is trans to this. So as a result, this CO cannot be migrated. That the new CO, what you have pumped into the system, that is being oriented in the cis fashion. So this CO can be migrated to the metal carbon bond, which is a known chemistry, and then you will be getting CO inserted this product. Okay. Now you pump in hydrogen into the system. So initially you pump in CO, followed by you pump in your hydrogen, and then you are getting this product. Okay. And you look at the 16 electron, 18 electron here, again 16, again 18, and rhodium oxidation state, you look at this way. Okay. It is going on, and then here you have 16, then it is 18. Okay. And then it is 18, and you see the rhodium oxidation state here 1, here 1, here one, here one, here one. You have to remember this thing. Here again 3. And then the hydride transfer takes place and you get back the catalyst and you get back the formylated aldehyde product. Okay, so these 2 steps are similar. And here also you look at the phosphine orientations, the mutual orientation. Like hydrogenation, you are getting transpositions, you are getting cis position, then you are getting alkene addition, then you are getting hydride transfer. So in the formylation case, you are then inserting CO, and then CO is being migrated, okay, to the metal carbon sigma bond. That is important. CO is actually migrating to the metal carbon CO bond, and that is possible if they are in the cis orientation. If they are trans, that migration is not allowed. Okay, and then you pump in hydrogen, and then again metal hydride transfer would take place, and as a result you will be getting back the product. That's why I'm telling you, if you have metal hydride compound, which are very important. Now again you need to remember the first transition metals, if you take, the metal hydride formation is not so simple. Okay, you won't get a metal hydride based complex so easily. But if you go to the heavier metal based compound, then metal hydride is one of the common factor over there. And it is expected that metal hydride is that compound would be a good catalyst for your hydrogenation or hydroformylation reaction. But that's a very generic statement I am making. This statement has of no value until and unless you taste that particular compound for the hydrogenation or for the hydroformylation reaction. Because you have noticed that the movement of the other groups present around the metal centers, that is very important, because they are moving from trans to cis, cis to trans, all sort of things happening. Now, if you take, instead of monodentate phosphine here, if you take one bisphosphine, okay, that means the one chelated phosphine, then you will see the whole purpose is drained off, is gone. Why it is gone? Because in the process you need to create a lot of space, okay, so the substrate can bind, so that your hydride can be transferred properly, or CO could be transferred properly. Okay, and then once you pump in CO or hydrogen gas, they could find chance to bind in between. So many parallelly operating factors you need to take care. Then only you can expect to have it. So in the beginning, you may have one hydride and you could start believing that this would be functioning. Could be possible. But in science, what happened, you cannot draw any line before you test it properly. And if the process is reproducible, that means you can keep some trust or some confidence on the compound and its activity. Okay. Now, if you see again, the hydroformylation is favored at the terminal position. Now, if you have the terminal alkene, then it would process very nicely. There is no problem. But you may want to have the hydroformylated product out of your internal alkene. Then what will happen? As you know, that alkene isomerization takes place, na? So it will first undergo the isomerization from internal to terminal, and then it will undergo your hydroformylation reaction. So all possibilities are there. So if you start with the terminal alkene, that's a simple form. Then immediately it will be hydroformylated and you will be getting common products, right? Aldehyde type products. Now, what would happen if you don't start from a terminal alkene, still wanted to have this, hydroformylated product? Then the terminal and internal alkene, if you started, and then internal alkene could be isomerized before hydroformylation, to the terminal, and then it could undergo the hydroformylation reactions. Now here you must have noticed that we have this particular intermediate. Nah? So if you go to this, yeah, this is that particular intermediate we have. Yeah, we have over here. Now here we have pumped in hydrogen. Nah? For this catalyst, we have pumped in hydrogen, and hydrogen gets links to the metal center, and then hydride transfer, then product formation, and you are getting back your catalyst. Right? Now, if you at this stage, instead of hydrogen, okay, instead of hydrogen, because this is the electrophilic center, if you use the nicophile like OH group, or if you use the OR, okay, or if you use the NR2, then what will happen? Your product would be either acid instead of aldehyde, or esters instead of aldehyde, or amides. So you can have variety of products out of this. Now what happens if it is a rhodium, if you put it over here? It has been observed that is very selective for hydroformylation reactions. It will not give you this kind of product. But if you take palladium, and it has been observed that at this point, if it attacks or it reacts with variety of nicophile, and it gives you different kind of products. Okay, it looked very simple, but utility was enormous. Okay, enormous utility, right? So what I'm trying to mean, it passes to the same intermediate, but your nature of the product could be made different by using different nucleophile at this point. So the message is, don't take it granted that all metal complexes would behave identically. Not really. Okay. As you see that, that so many factors are involved in moving from here to here. Okay, on a piece of paper, we write from here to here with a catalyst. But if we try to understand the mechanistic approaches, and if you not only understand, if you can establish the each and every intermediate in order to draw the cycle, then we get the feelings of the intricate aspects around that reactions. It has the two impacts. One impact is that we understand that reaction. That means we are not following blindly. Okay, sometimes we can carry out one reaction. For example, when we deal with the students, so PhD students particularly, some students, they don't apply their mind. Okay, then we tell them that your presence is not needed in the class or in the lab. Because I can take anybody from outside and ask them to, we don't need any master's students. We can take any plus 12 student and ask that if you have two hands, please do this thing, and they would be doing it. Okay, but the good students, their approach is different, but they apply mind in each and every step, right? So you need to understand each and every step. Okay, if you understand each and every step, that means what is happening, that at the end of the reaction, your catalyst may not be the best possible catalyst in the world. Okay, it may give you say 50% yield. Okay, with a decent turnover number. But you may be knowing that some other company, they have a catalyst which gives you 90% yield with a not decent, with an exceptionally high turnover number. Okay, so you are carrying out the same reaction, only catalyst, because everything is patented. You will never get the access of that catalyst. Okay, so you are trying to generate your own catalyst so that you need not to depend on others, so that you can do your business. Okay, and then you need to improve. Then once you understand that what is your catalyst is good for up to a certain extent, but not the best. So in order to make it best, you have to make a lot of trial and error processes at the molecular level. So you have to change the ligands here and there, and see metals and also all sort of things. And nothing is generic, right? So in order to understand, you need to know this inner mechanistic states or intermediates. Once you know it, then you realize that this particular compound is good for this product. But as soon as you move into one example I have shown over here, the analogous compound is the palladium, you see the different kinds of products could also be obtained. And that is only possible to discover when you apply your mind. That's why the good student, bad student could be differentiated very easily. Good student always concentrate on the fact why, and how. Not that end result of the product only. Okay, end result, you can get it accidentally or otherwise. But once you understand the inner meaning, that how it is happening, why it is happening, then tomorrow you can come up with the better products or better catalyst in the sense of catalysis. So, and then people would be interested in getting your catalyst, right? Instead of getting others' catalyst. And this is how one could make a move in science. Okay, one more reaction I thought to talk about. This is a little bit complicated reaction. Beside your hydrogenation or isomerization or hydroformylation. Now, the purpose of bringing this particular example into the discussion front to give you an impression that how the catalytic processes goes on. It is once you understand it, you realize that a lot of intricate aspects are involved. So one needs to understand it slowly. Okay, it is not I'm asking you to understand everything. I'm just giving you an impression. Now it says that if you react alkene with the CO, you will be getting basically ester. If you or aldehyde, if we put H here, or if you use the alcohol over here, then you will be getting the ester. Okay, and this reaction will never take place unless you put a catalyst. Now it has been observed this is the best catalyst available. So it is a textbook item. So if you use the palladium acetate, this is the commercially available salt, palladium salt, which is available. Very expensive, but you need not to do anything. If you have money, you buy it and react it in presence of terminal phosphine and one acid tosylate. Okay, you can see this is the TSOH structure, and in methanol solvent, then you are getting one monomeric product. So they are reacting and they are giving you your carbonylated product. But the same reaction, if you carry out with a chelated phosphine, this is a monodentate. It binds to the metal with the P. Okay, monodentate, very strong pi acceptor ligand. Now, if you use the DPPE, that means the bidentate ligand, DPPP, that means it binds to this P and this P. That means 1, 2, 3, 4, 5, 6 member ring it forms. Okay, chelated ligand. Then immediately you will be getting one polymer. Other conditions are same. You see that other conditions are same. Only variation is monodentate. If you use phosphine, phosphine is needed. Pakka, phosphine is needed. Okay. Now you could argue this way, that way, that you can do so. But phosphine, without phosphine, the reaction will not carry out. There's a reason behind it, I'm telling you. And then monodentate phosphine, if you use, you would be getting monomer. One this will react and give you one carbonylated product, ester over here. Okay, if you don't use methanol, you will be getting the aldehyde. Okay, but if you use the your chelated phosphine, then immediately you'll be getting good polymer. This polymer is very useful polymer. Okay, it's called the copolymerization of CO and alkene. Very useful polymer. Now, question is, what is the difference between monodentate and bidentate phosphine in guiding the product nature? Monomer versus polymer. Well, you cannot answer this question if you fail to understand the mechanism. That's why I said in the previous cases that once you understand the mechanism, then you could answer so many, so many queries nicely. Otherwise, it would remain unanswered. Now, then initially that was their observation. Okay, that once you change the phosphine, you get the monomer to polymer. Okay, phosphine means change means monodentate to bidentate. Then the question comes, why it is so? Then they tried to do the reactions with a variety of phosphine-based ligand. You could see this is the phosphine, and they also tried with the chelated nitrogen-based ligands and etc. etc. So there are three requirements. One is chelated bidentate ANSA ligand, which is necessary to get the polymer. Okay, and second is it has to be cationic compound. Okay, either mono or di, depending on what kind of ligands and co-ligands you are using. Cationic. Why cationic? Cationic means it would be more electrophilic, but it won't be too electrophilic. If it's too electrophilic, your reaction is essentially alkene versus CO. So at one point of time, the CO has to link to the metal, and then it will be transferred to the alkene. Now, both alkene and CO must link to the metal. That is the role of the catalyst. Okay, it allows both the reactant CO and CO and alkene to come closer and to participate in reaction. I have given that examples. Now, it's in the absence of catalyst, they will remain far away from each other, and then there won't be any reaction. So it provides an alternate platform where the reactants can come closer and they can participate in internal reactions, and that is how it is happening. So CO would bind with the palladium too strongly. If it is too electrophilic, then it cannot be migrated to the if we put alkene over here. So there are so many conditions need to be satisfied for a catalyst to become a good catalyst. Okay, these are the points what it is being written over here, and try to understand the mechanism. Now let us assume that you started with the palladium. This is the diphosphine. This is the sketch of the diphosphine bidentate way, and you have one hydride, and you created one space over here, and then alkene binds over here, and then hydride migration. Already we know this is cationic, slightly electrophilic. That's why. Then hydride binding or migration will take place. So cis orientation is needed. Then you'll have metal alkene, and then CO comes. I said that both metal carbon, alkene, and CO needs to be linked to the metal. Then CO binds. Okay. And then what is happening over here, that the CO, this is metal carbon, this is metal carbon. So the CO migration takes place. Okay. And as it is, or what happened, the alkyl migration takes place between the metal carbon bond, and you see, you will have this carbonylated product. Okay. Now, since you have used the diphosphate, instead of the product getting out, then it reacts with another mole of, sequentially, alkene and CO. And the same operation now goes on, and the chain grows. And then this process continues, chain grows, and at one point of time, you can truncate this bond, and you will be getting the polymer. Okay, what you need to. Now, still I have not answered the question. The question is that if you use the OMe over here, then you could see that this would be migrated, OMe over here, and then this path would be different. Now, if you use H, then they have observed that alkene first react, and then CO, and then CO migration. If you use OMe, then first CO comes, then this CO migration takes place, then alkene comes. So the order gets reversed. First alkene, then your CO, and here first the CO and then alkene. Okay, but alternate way. So one CO, then alkene, then CO, then alkene. It is not that CO, CO, alkene, alkene. I will say why not. Now first let us answer the question that why diphosphine is needed to get the polymer and why monophosphine facilitates your monomer. If you use the monodentate phosphine, then what is happening? That alkyl would form the way it was formed with the hydride product you have shown like this case. Yeah, this case, alkyl would form. Here it is, we consider monodentate now. Now, if it is a monodentate, then these could be in equilibrium with the transphosphine. So cis-phosphine and transphosphine would be there. Now, if after CO migration, then what will happen? The trans is the favorable condition. You see the arrow, maximum arrow in the trans position, minimum in the cis position. Once it is trans, then the second alkene attack cannot take place. Okay, so first alkene, then CO, then you get the product, and trans disposition of the two triphenyl phosphine does not allow a second alkene to come in contact to the metal, and as a result, it gives you the monomer. In presence of solvent, it gets solvated, monomeric product. But if you use the bidentate phosphine, then it will never become trans. Okay, bidentate, this equilibrium won't never be there. Bidentate phosphine means chelated phosphine. It will always remain in the cis. That means you will have this vacant site at all point of time. Every point of time you have the vacancy, so that it can participate one after another and allow the chain to continue. Now, how long the chain could be continued, it's up to you. There are mechanisms by which you truncate it depending on your need regarding the length of the polymer. Okay, so this is the problem. If you use the monodentate phosphine, then at a particular point it can become your trans and cis together, and the trans would be dominating, which won't allow the second set of alkene and CO to come in contact to the metal to participate in the chain growth process. But if you use chelated phosphine, the chelated phosphine would always remain in the cis position. So always the second or third or fourth or fifth alkene and CO reactant would find the opportunity to interact with the metal center and to participate in reaction, and it would allow the reaction to proceed to give you the desired polymeric product. Now the second point what I said, that sequential addition instead of simultaneous addition. That means alkene and CO and alkene, that sort of addition would take place. It's very, you find why it is so. It could have been CO, then alkene. No, it should be one pair first, then another pair, then alternate another pair. The reason is that if you say you consider this is one product, the polymer is formed, which is the polymer means I'm talking about here. This thing is being formed, and then one CO comes, and then CO addition takes place. Now, if you add the second CO, what is happening? Second CO will bind to the metal. How it will be migrated? CO could be migrated to the alkene bond only, na? And this CO cannot be migrated over here, right? So it will remain as a monodentate compound. Sorry, as a mononuclear compound, where this bond may be dissociated, but it cannot take part. Now, if you react this with the alkene, you see that alkene reacts, and then the migration takes place, and as a result, you will have the acrylate intermediate. And that intermediate, you see that oxygen disposition is such, the oxygen is linked to the palladium site. Okay, this way. Now here, if you add one more of alkene, okay, I'm talking about sequential addition. So this is one more of alkene added, and this is the product formation takes place over here. Now, if you add one more of alkene, that means this bond has to be dissociated. Now, metal oxygen bond and metal alkene bond, you have to compare the strength. So this strength is not strong enough to remove and add one more alkene over. That is necessary for polymer formation, right? Okay, that is necessary for polymer formation. Or it can have the beta hydrate elimination at this point, and then it could be transferred. That is also not possible over here. So it is crossed. So if you use that earlier pattern, that first you are reacting with the CO, you are getting the CO inserted product, then alkene, then you are getting this product. Okay, then one more of CO would be added, and then if you use another alkene, then the chain would start propagating. So the two factors we are talking about over here, that one factor is if you react CO and alkene, nothing is going to happen. No reaction. Because the activation barrier is too high, so it cannot be achieved. Okay. Now, if you add one catalyst over here, and you have to choose the catalyst in a very selective fashion, that if phosphine is considered to be one of the finest candidates over here, and then if you use monodentate phosphine, then one step reaction will be taking place. First step is monodentate phosphine, means they will be in the cis position, then CO binds, then alkene binds, and then migration takes place, and you get the carbonated product, but at the monomer 1 unit only. But if you take the phosphine, now what happened? That it will remain in the equilibrated position with the trans-phosphine position after one reaction, and that won't allow the second set of reactants to bind to the metal to allow the chain to grow. But if you use the bidentate ligand, it will always remain in a cis position. So question of trans in equilibrium won't arise. So always there will be enough vacancy or space around the metal center, but the second set of reactants or third set of reactants or fourth set of reactants to come closer and to bind and to participate in the reactions. And the second question was that what is the need of sequential steps? The sequential step, if you start, let us assume that you are moving into the moving into the 2 CO addition. So first CO is fine, that will link to the polymer. Okay, I'm sorry. First CO will bind to the metal, and your alkene would bind to the metal, then CO would be transferred to the alkene, and you will be getting carboxylated product. Now, if you add second CO, now second CO, because space is there, so second CO can add link to the metal center, but where it would be migrated? That is the question. It cannot migrate over there. No? So there, if you instead of that, if you put on alkene, that alkene can easily migrate over there and give you the product. Now the reverse way, if you try to understand, that if you use that first alkene, the alkenated product you will be getting. Okay, and then there will be an acrylate intermediate where oxygen of that product attached to the metal will link to the metal center. Now, alkene versus alkene, if you put it, alkene cannot remove that oxygen, because what will happen? Alkene initial binding is the pi bond, na? Okay, this is not that a strong bond. Okay, so that cannot, replace this one. But if you use CO, immediately it will get up and CO will be attached to it. So this is how one needs to understand the mechanism. So at the end of the talk, what I am trying to convey to you, catalysis is a very delicate process. You cannot avoid your basic chemistry knowledge. For example, I said bond breaking, bond forming. These are the two, integral part of the two integral steps of the catalytic processes. First one, then you will have oxidative addition, you will have reductive elimination. These are the part of the system. Third part of the system is your insertion and extrusion. Okay. And the fourth part is that insertion, if it has to take place, then there are mutual dispositions among the substrates, among the species which would be inserting on each other. Their mutual position. And also you need to take care the steric, electronic factor individually or in combinations. Okay. So if we put all the factors together, okay, I'm trying to say you in a very simplified manner. Things are not simplified as it is appears. Okay. So if you put all together, then you will have a better way to move in. And and to get one compound and to test it for one particular reaction, and it is happening, that is not enough. For every reaction in today 2020 or 2021, for every reaction there is a catalyst. Still people are trying to make newer catalysts for the same reaction. The reason is very clear, because the catalyst, what it is, we are trying to get the better catalyst. Every catalyst has its own drawbacks, okay, in terms of either turnover number or turnover frequency or mechanistic understand or yield or selectivity or cost, okay. So many factors are involved. So that's why people are trying to make every day the newer catalyst for a certain set of reactions, so that it will be commercially viable and it will be good for understanding, good for handling monetarily and also safety point of view. So there is a never-ending processes. So once you get a catalyst, that means you have cracked the point, okay, but not necessarily that is the dead end, okay. So you have to make a move, and in order to make a move, you need to understand the mechanistic aspect. And when you need to understand the mechanistic aspect, then you need to take the help of all the chemistry knowledge you have acquired so far. And if you put everything together, then only you can have a better perception. Otherwise, again, you will be going back to the square one. Okay. I think I should finish it here. So you go through all the slides. I want to just share a couple of more catalytic processes. Let's see. You just let me know that how to move on Monday. Just to discussion overall, or to some discussions and some some new events to also cover, and accordingly we'll cover it. Okay. Okay. Have a nice time. Stay safe. Keep well.
Thank you, sir.
Thank you, sir.
Okay. Thank you.
So.
So can I end the meeting? Yes.